So today we'll talk about rotational momentum, and so this is some guy trying with, I guess, probably liquid nitrogen, right? To put in a container, and as it warms, it will expand, and so it creates a gas source, just as it warms naturally. And he's got rabbit's ears tubes which screw into the top that you can bend in some direction while you'll sit. And it looks like he puts it in a beaker of water to warm it, and it'll float. And also that acts as a kind of nice bearing for it to be able to rotate. And so, if you can see, yeah, you probably, it's not super clear, is it? We've kept the lights on as well. There you go. You get the idea. So that's kind of the theme of what we'll talk about today. So I will hold that. Be a good topic to work on, actually. Let's see if this one works. Oh yeah. So, well, in German. So, a big problem with the grid is wind and solar is not dispatchable. It's not there all the time. And certainly the sun doesn't shine at night. And so storage through batteries or other things like pumped storage is an issue. Pumped storage, you put water when electricity is low price at night. You store it at high elevation, lots of potential energy, and then you release it when the demand is high, when everyone puts their toasters on in the morning or cooks their dinner at night. And so it allows you to have kind of large-scale, grid-scale storage that isn't a battery, because batteries are kind of expensive and use rare earth metals, etc. So it requires, as part of that scheme, like any hydroelectric scheme, some way to turn kinetic energy of the water coming from high velocity downhill using gravity to put it through a turbine and generate power attached to the turbine. And of course the opposite of that is the same turbine being used as a pump. You turn the pump by supplying electricity to it, and it pumps water up to the upper reservoir. And so that's kind of why we're interested in the ideas of I don't want to reply. We're interested in converting energy from one form to another. So from potential energy in this particular case to kinetic energy, for which we can harvest the kinetic energy to take it into electricity. And we saw this one already. It's kind of a cool example. A Pelton wheel. Some of these hydroelectric schemes work with these wheels, just a bunch of cups on a radius, I guess. And this is just hitting those cups with a jet of air on the left-hand side, and they spin. And obviously, you're turning linear momentum into rotational momentum, and you can use that to be able to generate electricity. Again, what else do we have that's kind of fun? Just all kinds of stuff. This is neat as well. I think, yeah, this is kind of different. I mentioned last time there's a guy in New Zealand who had this idea of had a pipe coming from up on his hillside, supplied water into an electric washing machine, and used it in reverse. It put it through the washing machine, the little turbine in it, to be able to generate electricity from the motor. And he filed a copyright claim against me on YouTube, and I had to take it down, and I had one strike against me for I think it's 3 months before it erases itself. If you get 3 strikes, they take your account down. But this is just an idea to take moving velocity of the water to be able to transfer that into rotational momentum, very slow, and it just fills up a portion of the pipe, and it's Archimedes' screw, basically. It pushes that water into some location. It's not using it to generate electricity, I don't think. I think it's using it just to pump water from the river to a higher level on the bank and use the power of the water to be able to do that, the flowing water to be able to do that. And so that's kind of a cool idea, I thought. And what is this? Oh yeah. And so I had a hard time finding this. I had a great one that has a dancing dog around it, a dog in a sprinkler. But this is kind of the object of what we'll do today. Obviously, it's a kind of a version of the rotating wheels that we've talked about. And this is the kind of punchline, I suppose. A lawn sprinkler, which again turns pressure from the water into flow out of the end of the sprinkler, and it turns the sprinkler into a machine. And just like last time, we talked about the idea of if you have a vane that you hold static, you're doing work against it, you don't do any work because it's not moving. Or if you have a vane that's moving at the velocity of the water that's being applied to it, there's no force applied, so again you don't do any work. So if you grab this vane and put some torque on it to stop it from rotating, then you'd actually be at this sweet spot in the middle, providing energy, getting work from the system in the same ways that we talked about last time. So that's kind of a potted history of what we're going to attempt today anyway. So we'll do an example at the end of it with a little device like this, because obviously it's a way of being able to, you could hook this up to a generator and you could generate power from that. You can imagine doing that. So that's the object of our interest today. So I'm going to set that aside. I'm going to go back to this. I guess there was another one here. I thought it was kind of interesting. Here would be a great project. So this is a paper in Nature magazine, top science magazine, talking about how you can use these fins that I guess are all arranged, not related to today's work, but just I thought it was a neat idea, that you can use these fins to actually generate waves that are much higher than the incident wave. It kind of magnifies them in some way. I guess in some way you can think about it working as almost as an optical lens that focuses things. This focuses the energy so that this wave in the center of these baffles, I guess, that are all pointing inwards, takes a motion of a wave, say, coming from the left, and it makes it into a much bigger wave as it focuses in the kind of idea of kind of a bit like a lever, right? You have a lever with a long arm and a short arm. You apply a small force on the long arm, it gives you a big force on the short arm. And so this is kind of a fluid dynamics aspect of that. Fine. So I'll let that run in the background. All right. So let's get on with this. To put us all back on the same page, I suppose, we're talking about conservation of momentum. So remember, these 3 weeks, conservation of mass was last week, conservation of momentum was this week. On Wednesday we talked about linear momentum, and let's recap that again just to get it all in order. The final part is to talk about rotational momentum, which is not really much of a stretch from what we've dealt with already. And then week 8 we'll talk about conservation of energy, kinetic energy. And so kinetic energy is useful because you can also use that to cast in terms of kinetic energy, chemical energy that you're converting into chemical and kinetic energy, such as in a jet engine by burning a fuel. So it's a link between fluid mechanics and thermodynamics, if you like, although we won't get into too much detail with that, with the thermo side of things. So what do we want to do? I think it's useful to do a recap of what we've talked about so far. So let me do that. So I'm going to draw the same diagrams that we've had before. We've had the idea of a vane. The idea of this. We have a reaction. We've talked about flow rates, say static, and the fact that we can divide V static into two parts. One is velocity of the control surface, and the other is the velocity across the boundary, right? So you know that we use that to write the static velocity is equal to the sum of the control surface plus relative to the boundary velocity, not a gunship, the fire tender. We have the idea that this is, again, I guess V 2, this would be V1, this would be area 1, this would be area 2. And we can define these static velocities that we see in terms of these components here, control surface and this. So I guess we could call this W1. I guess we could also divide this into the components that are related to the static velocity that we see. As a static observer, it would comprise a velocity relative to the control surface. In fact, all of this velocity would be relative to the control surface, right? Because the only motion can be horizontally. It has to be static in this direction from this geometry. And so the basic equation that we come up with is straightforwardly sum of forces. Is it cold and cough season already? Is equal to the velocity in the x direction times the mass flow rate. I guess this is a summation also. So that's the basic expression that we have. The mass flow rate is always given by the velocity relative to the boundary area times density. This is always relative to the static. And so this expression we can replace as being equal to, just by taking this term here, I suppose, velocity of the control surface plus W multiplied through by mass flow rate. And we kind of went through 3 examples last time. And so those 3 examples, to take them in turn, was, I guess, one was static. And static means that the velocity of the control surface has to be equal to 0, right? Because it's not moving. And I didn't draw that on here. I guess I should perhaps draw that. It would be... These are clearly vectors, but we are only interested in resolving in one direction at one time. And so let's not complicate life by noting that. So if we look at the static behavior, then this isn't moving. The velocity of control surface is 0. And if it's steady, so this was the same as our tube when we talked about conservation of mass. Control volume doesn't move, water flows through it, and so steady means that the sum of mass flow rates is equal to 0. So steady means mass in equals mass out. There's no net accumulation in the system. So if that's the case, we can always write this by taking this term out. And so I guess this expression is always correct. You've just got to decide what the terminology is that applies to it. And so this would be that so this would be the expression for that case. So all we've done is we've noted that this is 0, and so the product of those has to be that. So that's one of them. So perhaps I'll do it down this side. So that's the first of them. The second one was, so this was our tube. I'm just talking about the analog that we had when we talked about conservation of mass, was that we take a control volume and we'd have some going in and some going out. The second one was moving. And so the consequence of that was the control surface is not equal to 0, but steady. And so steady means that this isn't an equals. Steady means that sum of mass flow rates is still equal to 0. Right? Mass in equals mass out. If I were to draw a picture for that, I know this isn't kindergarten, but sometimes visuals work for me as well, perhaps they work for you. This was our jet engine, right? Moving. And so in this case, we need to use the full expression, that the force, sum of forces is equal to the sum of the velocity of the control surface plus the relative velocity. So in other words, just this expression again, mass flow rates. But in this case, because the product of these two terms, the sum of mass flow rates has to equal 0. So the sum of these equals 0, but it depends on what we're multiplying it by. But certainly if we're multiplying this by a single constant, and the control surface velocity can only be a single value, right? It's translating across the page. And so this means that the product of VCS mass flow rate equals 0. And if that's the case, then we can use the expression sum of Fx equals sum of W mass flow rate. We can get rid of this term here. And so this expression and this expression hold identically for these two. And if you want, we didn't go through it in class, but there's an example with a vane that does exactly that, and they use this expression exactly, what we've just used, and it kind of explains the individual components. I won't go through that further. We went through an example last time. And finally, the third is for moving. Oh, look behind me to see. Oh, it's not too bad. Perhaps green isn't the greatest color. So moving means that, again, the control surface is moving at a finite velocity, not 0. It's non-steady. And so that means that the sum of mass flow rates is not equal to 0. So this was our case of the decapitated cylinder with the fluid coming out of it. Clearly, there's an exit from this. There's not an entry into it, so it has to be being depleted with time. Maybe for short terms, we can think of it as the pressure not changing, and you'll have seen examples from prior classes and tests related to that. And in this particular case, we have to be, again, use the same expression, doesn't change. Velocity of the control surface, which is not equal to 0. The velocity of the fluid coming out of it, and the mass flow rate. And I guess the only point I'm making here is that now, since the sum of mass flow rates is not equal to 0, since the sum of flow rates is not equal to 0, then we can't do this little maneuver, and we have to keep this full expression. And the consequence of this full expression is, if you're trying to get an idea of how this works, and we talked about it last time, these are obviously vectors, so they have both magnitude and direction. So we have two end conditions, and we made the case last time, is if you put, in this particular case, we're talking about the reaction that you have to apply, which goes into this force. If we talk about the magnitude of that reaction, if it's 0, then the only way this can be 0 is if these are equal to the inverse of each other, 1 equal to the minus 1. Equal magnitude, but opposite direction, because the vectors are opposed to each other. And so if, no, we did it the other way, right? Sorry. Let's stick with the way we did it last time. I think we had velocity on the bottom. Doesn't matter, of course. And if the force is equal to 0, then by definition, the velocity has to be equal to the velocity of the gas coming out of it. And so we're at this point here, a maximum. And the converse is, if we grab the vane so it can't move and apply a force that stops it from moving, then the only way that this velocity is equal to the negative of this. And if we grab the vane, then this force is a maximum, and by definition the velocity of the vane is equal to 0. And so as we go through this, it's not necessarily a linear line, but if we take the product of those two, velocity versus the product of reaction times velocity, and of course this, I won't underline it, the units of this are going to be force, which is newtons meters per second, which is the same as a joule. Joule per second, which is the same as a watt. And so this, the product of this force times zero velocity is zero. The product of zero force times a big velocity is zero. And the magnitude of this is going to look something like this. And somewhere in here, you could calculate it if you had an expression for it, that the magnitudes would be what it is. But I guess the kind of take-home message in terms of feel for what's going on is that there are two end-member behaviors. One is when there's no force acting. The only way that it can have no force, if it's frictionless, etc., is if this incoming velocity is exactly the same as the velocity that's moving at, because then W will be equal to zero across this boundary. And if this is held so that this velocity is zero, then this force will be a maximum, and you can just get it from this static equation here. Very straightforward. Right? So those, it's probably useful to have a kind of idea of those two end-member behaviors. So that's kind of the potted view of what we've talked about so far. I guess I want to draw a line down here. I'm going to try and be fancy and move these over so that I can go down, and then I'm going to switch to a different color just because of the heck of it. So now, I'm not going to rely on, I'm always skeptical of how useful all these equations are. And so that's what we'll talk about now. It's actually a fair bit of time. And I'll go back to this, is exactly this. And so if you came in late and you, so this is just it's a bit more complicated because it's squirting up in the air, but you can imagine this being kind of in a horizontal plane. And this is now the same behavior that we talked about, but we could think of this vein that we've had this fluid coming in and then squirting upwards. It's convenient because it's at 90 degrees to each other, so the stuff that goes upwards has no component in the x direction. And so that makes the calculations a bit easier when we're demonstrating. But you could imagine this crooked end of a pipe that we have on this. It's angled in this particular case, but it could be at right angles. And you could think about how that drives the flow around. So you could think of the end of this as being an individual vein where water is coming along here and it's squirting out of here. The velocity it comes out of here is W. And the velocity at which the control volume is moving is the actual arm of the sprinkler, which is going at some different velocity. And so it's a bit like the vein, in that you could imagine if this was really a right angle that was going around like this, then the same conditions apply. If it's held, then the water will squirt out and it'll go across the room and hit the wall. If it's not clamped and free to move, it'll move around because of that fluid. And actually, it'll be a bit like, I'm not sure what the best analog, I was thinking best analog is like putting toothpaste down on the surface, is that it will move at exactly the same rate as the fluid coming out of it, just like the vein would. And so a drop of water will just be static at that location and would fall to the ground if it was a right angle degree. Because it would be moving away. It would just be dropping out the thing as you're going along. It'd be sitting on the road, and it would be like dropping stuff out of a truck, I guess. So that's kind of the geometry that we'd like to be able to look at. So instead of going through the theory, I'll try and put with dot products and cross products. Perhaps we can come to that if we have time at the end. But the idea is to perhaps cast this analysis in the same vein as our previous analysis. So it's pretty straightforward. It can be pretty straightforward. I'll try and make it so. And the straightforward idea is that we're talking about moment of momentum, so rotational momentum. And so you'll recall that we used Reynolds transport theorem. When we talked about momentum, our value of b was just equal to the velocity. What if instead of using a value of b, which is the product of velocity times a lever arm? And so let me draw that first. So what do I want to draw? I'm going to draw a vane that looks like this. And so, can I do this? I'm not sure. You can see where this is going, right? This is a radius arm. Let me call it lowercase r. This is the system that we have, which is a velocity coming in here, a velocity going out of here, w, and a force being applied here. So this is able to rotate, I guess. It will rotate at some rotational speed w. It will go through an angle, which is theta. So let me write that. W equals speed. So it's radians per second. Theta equals the angle. And I guess 2 pi radians a second is equal to 1 revolution per second, RPS. And v theta is going to equal the radius times the rotational speed. So this is the rotational speed, omega. So, and I guess the other equation we might know is the bad choice of work. Let's call it power. Power is the rate of doing work, which is just equal to the force times the radius. And this term here we'll call torque, multiplied by rotation. So this is force times length, Newton meters per second. Radians is dimensionless, 2 pi radians in a circle. And so this is the units of watts. So you're starting to see that this could be a machine where you could generate a certain amount of power from it. In our case before, we talked about this being the product of a force times a velocity. This is a force times a lever arm times rotational speed. The units are the same, so because the velocity is actually the product of the lever arm times the rotational speed, this term here. So this is our velocity v theta. Okay. So I'm trying to make the point that this is kind of analogous to this, just written a different way. But it's providing the force is reacting against the fluid that's squirting out of it. The equations that describe that are shown here. So we take Newton's law of, we take Reynolds transport theorem. We use a substitution in terms of velocity. We take velocity times lever arm. And not surprisingly, the term that we have here, we could just take this. We could multiply both sides through by radius. And this is the expression that we end up with. So I'm just going to write that down straight away. This is it here. And so if I write it below, it's going to be sum of forces times a lever arm. Let me not put the lever arm in. So this is our previous expression. Velocity in the x direction multiplied by mass flow rate. And all I'm going to do is pre-multiply both sides by radius. And then that defines our expression in terms of, this is a torque, a force times a lever arm. And this is just equal to our v theta m dot summation. And so that's the expression we'll use. And so you have those written, I think, immediately above this at the top of the page. This is this expression here. This, like our velocity before, was relative to a static velocity. This is always a static velocity. So this v theta is a static velocity. So if we wanted to, we could substitute this with our terms, which would be w theta plus v cs theta. Right? Same idea as before. So this is our new expression. And so what we could do is we could do a simple example to be able to define this behavior. So the example that we will do, so hopefully that makes sense in terms of what we're trying to do. You could imagine that if this lever arm goes to infinity, then the radius, the arcing radius is really shallow. It's basically a straight line. And this direction of this is really just a linear behavior. So in the limit, I guess, you could think of it as this case. So there's a definite connection between those. So let's try doing an example that uses this. I won't bother with the cross products and all this. I will note that there's a sign convention. It's at the bottom of this page. In the same way that we've been using a right-hand sign convention for X, Y, and Z in terms of thumb, first finger, and second finger, whatever they are. Then there's a sign convention called the right-hand rule for rotation. So this is the Z-axis, and rotation, positive Z-axis upwards, and rotation is positive in the direction of the fingers, is all it's really saying. It doesn't really matter. You can write it anyway for the equations that we're writing. We're just doing a simple one for one direction. But this is the idea here. So this is the idea of a sprinkler. It's set up a bit differently, but it essentially has tubes that come out from a solid mandrel. And the idea is this. Let's go through it. I'll do it in simplified form. So you have fluid coming into the center of this mandrel at 5 liters a second. So this is 5 times 10 to the minus 3 meters cubed a second, right? 1,000 liters in a cubic meter. It rotates around this point. The exit comes out at a variety of different angles. It could be at 0 degrees to the circumference, so in other words, tangential to it. If you increase this angle, I guess you could get it all the way to being 90 degrees. That would be the maximum. You can probably imagine that if you have it coming out at 90 degrees, it has no force directed along this way, so it wouldn't spin. And the maximum spin would be when it's parallel to this tangent. We have it has 3 nozzles. Each of these nozzles has a cross-sectional area of 18 millimeters squared. So I guess that's a millimeter is 1,000th of a meter. So this would be 18 times 10 to the minus 6. 10 to the minus 3 times 10 to the minus 3. And the question is, how big is the resisting torque required to hold the rotor stationary? And if it's released, how fast will it go? And so it's probably easier for us to just go back to that expression that we had. So let's do it on this sheet. So this is I'm just going to do it here. So we have, if I draw it out, actually I can do it below. See if I can draw it. See if that'll make a circle. Wow, fantastic. So if we have this, you can kind of see where this is going. This is theta equals 0. In this particular case, we said if we're doing it the correct way, I guess our positive rotation would be in this direction. It's got a center to it. This would be positive rotation, omega. This would be the radius that we have. And the expression that we want to honor is going to be the sum of the torque is equal to the sum of the radius times W theta plus VCS theta times mass flow rate. So if we take it, we've got 3 nozzles, 1, 2, and 3, just like this. And so what do we know? We know that Q is equal to 5 times 10 to the minus 3 meters cubed a second. I guess we know that then W is equal to Q over 3. It's going to be equal to Q1 over area. So area was equal to 18 times 10 to the minus 6 meters squared. And we're going to have to accommodate, this would be the velocity that's coming out in this direction. And so if we wanted to evaluate the part that is in this direction, this would be W coming out here. So W cosine alpha theta would be the direction of this component with the right angle to here. So this would be cosine theta. And I guess we know also that the control surface in its velocity, I guess the little thing done, this would be the velocity of the control surface. The control surface has to be going in this circular direction, has to be tangential at each of these points. So I guess we also know that the velocity of the control surface, we can also write this as the radius times the rotation rate. And so what we can do, I suppose I can write it out, is that sum of this, I don't think we'll do the mathematics of it, is going to be equal to the radius, which we know, I can't remember what it was, so we can look at the question again. W theta is going to be this term here, plus VCS theta times mass flow rate. So each of these terms then, this would be one term. So we know what this is, we know the area, so we can calculate what this flow rate is. It's a third because there are 3 of them, so this is per nozzle. And so I guess we have to well, this is just a velocity, so that's fine. That's the velocity that's coming out. We have this one, which I can do as this. We have a radius, presumably we know. We can apply, this could be either 0 or we could determine what this is. I guess that would be the object of finding out what it is. And we have a mass flow rate. So mass flow rate is going to be equal to Q over 3 times density of water. So meters cubed, so in terms of the units, meters cubed a second, kilograms per meter cubed, and this is going to be the mass flow rate totally. And so we could divide through by 3 to get it per nozzle, but we're going to have to multiply by 3 to get it for all 3 nozzles. So those cancel out. So we could just, mass flow rate is just going to be Q times rho. Volumetric flow rate multiplied by this. This is because there are 3 nozzles, and a third of the flow rate should be coming out of each of them, but the mass flow rate has to be the total amount of mass that's coming out. So those cancel, and so we'd know what this is. And I guess we need to know that this has to be, this also has this term in it here. So that's it. So we can do 2 things. So the end member behaviors would be when it's unclamped. So there's no T is equal to the force multiplied by the radius. So if the force is 0, then the velocity of the control surface is going to equal W, because that's the only way that this can equal 0. So these are going to be the negative of each other. And so when it's tangential to this, the flow rate W coming out of the thing is going to be exactly the velocity of the circumference of the arc of the thing as it goes around. And if we want to, we can convert that velocity into a rotational speed. We can do that. So this is the first condition. The second condition is if the control surface velocity is equal to 0, in which it's clamped, and then T theta is the maximum. And so this would be 0 in this particular case, and the rest of the terms we'd know, because we know the flow rate coming out of it, we know all the terms in here, we know the flow rate coming out of this, we know all the terms in here. And so those are the 2 kind of end member conditions. But of course we could say that if this is the maximum torque, we could also say that, say we set the torque equal to T max over 2. Got an ant crawling on me. And so that means that we're not clamping it, but we're releasing our grip enough for it to turn. And as a result of that, it gets to go at some speed, not 0 speed. Obviously, this is positive. The directional doesn't matter for the cases we're taking. And so in this case, clearly it would be going at a negative velocity. VCS would be negative. And so that's it. That's kind of it. It's no different from the things that we talked about in terms of understanding it linearly, because on a big arc, it is kind of a linear system. And so the example is there. So perhaps having done that, let's have a quick look at the example, just to see how the question plays out. So the idea is that this is the expression that we had. The torque is equal to the mass flow rate, the lever arm, times the relative velocity of fluid coming out of it. We can calculate the mass flow rate as just the volumetric flow rate multiplied by density. The velocity coming out is just going to be the mass flow rate per nozzle divided by the area of the nozzle, which is the velocity coming out. And if we substitute this and this into here, then we get this final expression. So this is for the case where it's held static. In other words, when VCS equals 0. If we don't want VCS to be equal to 0, then we have to have this term here being equal to relative to the boundary velocity plus the velocity of the control surface. We did that already, right, in our equation. We kind of included it all in one. We didn't exclude it. So we included it here all the time and then just looked at the different conditions. I don't mean to give you heartburn by looking at this. And so if we write it here, this equation here, if I keep them both on, is identical to equation 1, where the only change is that this velocity has been replaced by something a bit more complicated. The velocity of the circumference as it goes around, and the velocity of the fluid as it comes out, corrected for the fact that it's coming out either at cosine 0, which would be 1, when it's parallel to the arc, or at an angle which is slightly out from that as you go around. And so these are exactly the same equations that we just defined. And so let's not dwell on the calculations, but let's look at the result. They do the result for 3 cases. The first is where, oh, love it. So they have the case where this is equal to, this is theta. And so theta equals to 0 is tangential to this. You'd expect that that would be kind of the maximum effect, right? Because if you're squirting out on an arc that does this, then that has the most force in the tangential, right? Certainly you can see that if you're squirting like this, it has no motivation to rotate at all. So that would be the minimum force that you'd have to apply to keep it static. But here, this should be the maximum. So if theta is equal to 0, if you go through the calculations, you end up with a torque that you have to apply such that the control surface is not moving, and a velocity that results if you release it. And so 185 rads a second and 231 Newton meters. It's not force, it's a torque, right? A force times the lever arm. So this is the torque. If we do the calculations for 30 degrees, then the numbers, if I pull them out, come out to be this. So 200 Newton meters and 160 radians a second. So these are theta equals 0, theta equals 30. It's going the direction you expect, right? It takes less force to stop it from moving, and it travels at a lower speed. And if you do it for 60 degrees, then it becomes even less. It's 116 Newton meters instead of 200, and it's 92 radians a second in terms of velocity. And so you can see that these are decreasing all the time. If as I said, if you now do it for an angle of theta equals 90 degrees, then what would you expect? So the water's coming out, this would be the radius. So here the water is coming out at some rate, W. So W is finite, right? Because W is just equal to the volumetric flow rate over 3, because there's 3 nozzles, divided by the area of the nozzle. That's all that is. So this is certainly finite, but in terms of its component in its velocity in this direction, cosine theta 90 degrees times W is going to be 0. And so you'd expect that there's 2 things, right? Just by inspection. You'd expect that the torque that you have to apply to stop it from moving should be 0, because it's not going to want to move. And you'd expect that the velocity of this, if you release the torque, is going to be 0 as well. So that will just come out of this expression. And so that's kind of it. And so I guess the point I'm making is that you should try and understand this. The easiest way to understand the moment of momentum equation is just by drawing an analog in your own mind with what we've done for static vanes. And it looks just like a static vane, but the way it's turning in the limit, when this is a very big number, is just a straight line, because the arc is so shallow that it just moves in a direction. But this clearly allows you to take care of the moment of momentum behavior. And the idea is that if you have a torque, from that torque we can calculate the power that's generated. And it's exactly the same as before. This bad choice of terminology, W dot is equal to power. Not anything to do. Uppercase W. I guess the others, these have been kind of uppercase W's as well. I guess they've been lowercase. So the product of the shaft torque times the rotational speed, radians per second, newtons times meters is the torque, times 1/seconds is newtons meters per second, and this is the amount of work. And so you could count the amount of work. If we're in a turbine blade, if you're allowing it to spin freely with no generator attached to it, it can do whatever speed it's done. You'll never generate any power from that because it's rotating, so the angular velocity is finite, but the torque that it's generating, there's no resistance against it, so there is no torque applied. If you clamp it shut and stop it from rotating completely, then this rotational speed will be 0, even though you have a big torque on it resisting the wind, and again you'll generate no power. But if you allow it to rotate and have the drag of the generator motor attached to it, then that's in this sweet spot in the middle where you can actually optimize the recovery from it. And so lots of systems work that way. So that's it. So I don't know if that's better or worse. Certainly you can count your blessings in the fact that we haven't gone through cross products and etc. The Reynolds transport equations allow us to write a general equation, which I'm not going to go into, where these are cross products. And like dot products, which we dealt with before, the definition of a cross product is merely the fact that if you have a vector v, which is in space, so this is going in the negative x direction, so the direction of this vector would be -1, 0. -1 in the x direction, 0 in y, and 0 in z. So this would be the flow. If you have the location where that is applied, so this is the radius at which it's applied, so the radius would be 0 in the x direction, radius r in the y direction, and 0 in the z direction. So this would be the vector that defines this lever arm. Then the cross product of those, if you remember it from your calculus or algebra, I suppose it is this determinant of this equation. And this just gives you a force or a velocity times a lever arm to define this lever arm. That's all it is. And so this term turns up, of course, in this expression. This is torque. This is the lever arm. This is how we deal with it. I guess I'm going to go back here. This is where it turns up here. So this is a radius times a velocity. They're both vectors. And in its simplest form, we can think of this radius times the velocity just being this radius times this velocity. And we can think of this lever arm that goes into the torque equation here as being this radius times the force that's tangential to it. So that's it. So it can be very complicated. As complicated as we want to. This is kind of a general expression. The only expression we'll use is this. So that's it. So that's it. So that's conservation of momentum. Have a look at that as you wish. We won't talk about turbines, but you can imagine how it all works. And then next week we'll start talking about the third conservation equation. So mass was week 6 last week. Momentum, both linear and rotational, was this week. And then next week we'll talk about conservation of kinetic energy. And so the reason that's important is that everything we've talked about so far has with no frictional losses within it. So we've used Bernoulli equation. Bernoulli equation is inviscid, so the upstream potential is equal to downstream potential. There's no loss. In real systems, there's actually loss in the system, and so dealing with kinetic energy, what we'll talk about next time, is a way for accounting for that, which is a very real, it's the essence, if you like, of dimensioning pumps and looking at flow in pipes, true losses. So that's it. Great. Well, all right. So hopefully that was clear. So you'll get another week 8 thing tonight. There's week 8 is in class. Week 9 is our midterm again. The midterm stuff's posted. You'll see that there's stuff in the midterm on linear momentum. There is nothing on rotational momentum. Doesn't mean you should turn your brain off to what we talked about today, but you'll see it. So the video is posted, so you can have a look at that and you can ask questions next time. Same format as before, but not next week, it's the week after, to give you a good start. Okay?